Let's now look at the excess properties approach for evaluating non-dilute liquid mixtures. And so in Chapter 8, we talked about, if we have the molar Gibbs energy of a mixture, we could split that into the ideal sort of solution mixing plus the delta G of the mixture as well, right? So that accounts for the non-ideal mixing a solution. Okay? Now for each of these terms, we know that the Gibbs energy is equal to enthalpy minus temperature times entropy. And so we could split up these two terms in terms of enthalpy and entropy. Okay? And so we have the enthalpy terms minus the entropy terms. Okay? And if we rearrange this a bit, we could write the equation like this. Plus delta H mix minus T delta S mix. Now for the ideal solution enthalpy and entropy, those values would just be the weighted average of the molar enthalpy and entropies of the pure species. Where C is the number of components in the mixture. Okay? And we could rewrite this term just as, or like this, where we could just say, okay, this is the weighted average of our Gibbs energy, molar Gibbs energy of each of our pure species. Okay? Now for this minus T delta S mix, right? If we were dealing, or in Chapter 8, we saw that this delta S mix term was just equal to RT times the summation of xi ln of xi. So if we revisit our molar G term, we could rewrite it like this. Xi Gi plus RT summation xi ln of xi plus delta H mix. Okay. All right, and so this is, we rewrote G molar in terms of this equation. Okay, and so we could group these terms into different categories. All right, and so for the first two terms here, this is what you would get for ideal mixing, if you will, right? And so you have the weighted average term plus the entropy that you get just from rearranging the molecules in your mixture. Okay. Now for this delta H mix term, this delta H mix term would account for what we call non-idealities in your mixture. So differences in molecular interactions or differences in molecular sizes. Okay? All right, and so these terms fall into different groups. And so when we think of the molar Gibbs energy for the entire mixture, we could rewrite it like this. C xi gi plus RT xi ln of xi. And then, for the last term, instead of writing delta H mix, we could just rewrite it as G excess, or otherwise the excess molar Gibbs energy. Right. Call this equation 1. All right, and so the way to think of it is if you have an ideal solution, your excess Gibbs energy for that solution would be equal to 0. And for a non-ideal solution, your G excess would be equal to your enthalpy excess minus T entropy excess. Okay? Where your enthalpy excess would be your, change in enthalpy upon mixing, and your entropy excess would account for changes in molecular conformations or molecular sizes. Okay? All right, in any case, so this was just the molar Gibbs energy of the entire mixture. But if we want to calculate the chemical potentials, which serve as that equilibrium criteria for mixtures, the chemical potential for species I, we know, is the partial derivative of the total G, or N times G molar, so that's total N. Partial derivative with respect to Ni, so at constant temperature, pressure, and species J not equal to I. And so what we're going to be doing here is we're going to be taking the partial derivative of this equation up here. Okay? So what we get is Gi molar Tp plus RT ln of xi, and then plus the partial molar Gibbs excess energy. Okay? Where, for this term, we could think of it as just our standard state chemical potential. Okay? And this partial molar Gibbs excess energy is the partial derivative of the Gibbs excess term at constant temperature, pressure, and J not equal to I.